Okay, so we're continuing with our chain rule today. And the chain rule, okay, we're going to be working with today is we use it in situations that are kind of given in a little bit of a different way. And I'm just going to read the intro here. It says, we need to be able to apply chain rule in situations where the two functions are given separately. So you know how when we talked about composite functions, you have the function f and the function g, and you kind of put them together to create the composite function. But what if you're given them separately? Isn't it easier to work with two separate things that are maybe easier than one complicated thing? In some cases, that might be, the answer might be yes. So in these cases, it's useful to use the Leibniz notation of the chain rule, or the Leibniz notation version of the chain rule. So the thing that you're going to notice here is another letter makes an appearance. Usually we're used to just y and x, but there's a middle letter that kind of is in the middle of between y and x. So if you read the first part of this intro here, if y equals f at u and u equals g at x are differentiable functions. So notice that the independent variable of y is u, but then u is the dependent variable in u and g at x. So if you think about it, just so you guys can kind of see this, if y is f at u, but u is g at x, can you see why it's still a composite function? It just I'm keeping them separate. What have I done here? I've eliminated u from the situation when I write it like this, but if I leave them separate, I need this u to kind of be the link in the chain. What? Link in the chain between y and x. Hence, we're going to use this version of chain rule. So it's Leibniz notation. So remember, how does Leibniz notation work? It's dy by dx will be dy by, well, what's y going to be a derivative of? Y is going to be dy by dx by d. So it's whatever the variable is. So if I have the function y equals f at u, the derivative of y with respect to u, so dy by du, and then I'm going to multiply, that's the derivative of the outside, or the outside function, and then times by the derivative of the inside. What's the inside function? Du by dx. Can you see how the u is the link in the chain there between y and x? Okay. So in other words, what this means is, if you multiply the derivative of the outer function in terms of u by the derivative of the inner function in terms of x, you're going to get an expression that has u's in it and x's in it, but this will represent the derivative. And then and then we'll do some examples to kind of get a feel for this, but then we can use that to answer more difficult questions like find the equation of the tangent, find the location of the horizontal tangents, all that kind of stuff. Okay? So let's do a few. So if y equals the square root of u and u equals 5x squared minus 11x plus 11, determine dy by dx. Then determine the slope of the tangent at x equals 2. All right. So here's what we're basically going to do. Here's the first thing. So we want to find the derivative of y with respect to x. So I'm going to write dy by dx. And the first thing I just want you to get in the habit of doing is just write that chain rule with Leibniz notation as step 1. So dy by dx is dy by du times du by dx. Okay, now, for this scenario, this is what I like to do, and I think it's the easiest way to kind of do this. I would like to just put dy by du into a set of brackets here. I like to put du by dx into a set of brackets there. I just literally want to, I just want to put the final dy by du and du by dx into these square brackets. So I recommend to do an aside to get the pieces. So the idea here is we're going to find the derivative of each piece separately, do any simplification I need to do over here, and then go put the value into the expression. Okay? Is this making sense so far? So dy by du. So I'm going to start by just copying. Y equals square root of u, or if I'm about to take the derivative of that, that would be u to the half. Good. Now, dy, I know this is the thing to get used to. We're so automatically going dy by dx, but it's not an x, it's a u. So dy by du equals, but u it just acts like an x. It doesn't really matter what the variable is, it's the rule that you're applying. So if you have x to the half or u to the half, it doesn't really matter, you're doing the same rule. It's the power rule. What's the derivative of u to the half? Half times u to the negative half. You guys get the nice thing here is you don't have to worry about the inside because it's just a u, right? That's the nice thing about doing it like this. There's no inside to it, right? The inside is kept separate. We've separated it out, so I don't have to worry about it right now. So half u to the negative half. So by now I think we're hopefully all very comfortable with saying, well, that's just 1 over 2. And then u to the negative half would become the square root of u in the denominator. Yep. Here's the deal, guys. From this point on, if you want to go directly, if you see square root u or square root x and you want to say what the derivative is, if you just want to jump right to write this, I would take it because it's one of those simple ones that you might just want to memorize. Okay? If you don't, if you want to do this every time, totally fine too. But I'm just saying that's allowable if you want. So there it is. So do you guys get that? I can now just put that right here. There's the derivative of y with respect to u. Done.
Ms. Antonin, please contact the main office. Ms. Antonin.
So u equals 5x squared minus 11x plus 1. Is this, again, an easy enough function to take the derivative of? Du by dx, this time x is the variable, so 5x squared derivative, 10x, negative 11x, derivative of 1, 0. So 10x minus. Okay. So right now, okay, we are almost done up to there. The only problem is that the question wants us to find dy by dx. And what do you notice is currently in my expression? There's like an intro, there's something in there that doesn't really fit the definition of saying, I want dy in terms of the derivative of y with respect to x. What do you notice is kind of like, ew, that's annoying. There's something in here I don't like.
You still have a u.
There's still a u. We don't like u, okay? So, man, I wish I had something I could replace u with. I wonder if there's something I can replace u with. That's u, right? Okay, we like u. Okay, so we're going to go. Now, again, this is where you can kind of clean up too. Could you put the 10x minus 11 in the numerator? Make it a single expression. So the 10x, I don't know why I did it that big, 10x minus 11 all over 2. I have to replace square root of u with square root of 5x squared minus 11x plus 1. Okay. Now, please don't write, we're not done this question, but just take a pause for a moment. I'm just going to let you copy that, and then I want you to take a pause for a moment just to recognize something. Essentially, do not write this, okay? Did you just take the derivative of this? Did you just take the derivative of that? Well, what would happen? Again, you're not writing this. What if I say, okay, you're taking the derivative of that? Say, forget about this u business. I just said, find the derivative of this. You're going, okay, rewrite 5x squared minus 11x plus 1 all to the half. dy by dx equals, this is, you guys get, now you have to use the rule from yesterday, because now we have stuff as the inside. Blah, remember our good old friend blah. Blah to the half. Derivative of blah to the half is half times blah to the negative half. Don't forget derivative of inside. Derivative of inside is? Okay. And then if you clean this up, you get that we're going to get the exact same thing here. What's the only thing that's going to stay in the numerator? 10x minus 11. The 5x squared minus 11x plus 1 gets put in the denominator and square rooted, and there's a 2 in the denominator. Ta-da, it's the same thing, right? But what's the complication here is you had to remember about the derivative of the inside, and it's just one complicated thing versus two pretty easy things. Does that make sense? And so And I'll be honest with you, the two pieces right now were easy. What if it got more complicated, right? Then you might be a lot easier to work with two smaller complicated things than one giant really complicated thing, right? So that's the idea here. So you have correctly answered the first part of this question by finding dy by dx. And then the question said, then determine the slope of the tangent at x equals 2. Is that an easy question to answer now? You have the derivative. What's the next part? Just put in 2. So I'm going to remind you of the Leibniz notation way of showing that. You guys, I know it's wonky, but you rewrite this. You do the little bar, and you write at the bottom of the bar x equals 2. That's symbolically saying take this derivative and put in x equals 2. If you don't like that, if you just want to write let x equal 2, that's fine too. You don't have to do this symbol, okay? Equals, and so now it's just a plug and chug, right? 10 times 2 minus 11 over 2 square root 5 times 2 squared minus 11 times 2 plus 1. So 10 times 2, 20, 20 minus 11, 9. Over 2 times the square root of 2 squared 4, 4 times 5, 20, minus 22. Oh, ew. Did I do something wrong? You guys see why I'm not happy right now?
Yeah.
Okay, so here we're gonna do a quick edit, because if I make, okay, see the 1 that was all the way through here, guys? It's a 6 now. So what happened? Because you guys see what's gonna happen. If that's a 6, what's the derivative of 6? Still 0. Okay. So there's a 6 here. There's a 6 here. There's a 6 here. Do you guys see why I picked 6? Because now it's 9 over, so 20 minus 22, negative 2. Negative 2 plus 6 is 4. Square root of 4 is 9/4. My apologies about that. But there he is. Okie dokie. So that would be the slope of the tangent there. And if you had to, could you then find the equation of the tangent? Okay, well, maybe I'll throw that at you. So if you had to find the equation of the tangent, you have the slope. What would you have to do to find, what other piece of information do you need for an equation of a tangent? You need the y coordinate, right? You have x is 2. Do you get that? You have to let 2 travel through both functions to get the y. Because y doesn't show up till here. You put 2 into there. Okay, we know what we just got when you put that into there. You got the 4. And then you have to put 4 into there and square root and get 2. Does that make sense? So 2, 2 would be the point. There's your slope. Y equals mx plus b, or y minus y1 equals m times x minus x. Okay. Okay, let's do another one, another few, just to keep practicing. So if y equals u cubed minus 4u squared plus 3u minus 2, and u equals the 4th root of x, determine dy by dx. Okay, so again, if you have to use Leibniz notation and you want to, whenever u shows up, whenever u shows up, you have to use this notation with the u in it. So, can you put that away, Michael? Okay, so dy by dx equals dy by du times du by dx. You write that on your paper. I'll give you like a pity half mark. Okay, yay, you know the model. But now we need to put the pieces in. So maybe this will help, guys, if we do a little separator here just to keep our work organized. So if we do an aside, okay. So the aside here is, so again, you don't have to rewrite y if it helps you. Do I really need to do a rewrite of function y here? It's just a polynomial. I don't really need to copy it. If you want to copy it and then take the derivative underneath it, fine. Or you could just take the derivative. Dy by du equals Derivative of u cubed, 3u squared. Derivative of negative 4u squared, negative. Derivative of 3u plus 3, and the derivative of negative 2, 0. dy by du found. Maybe for u, we do want to do a rewrite, just to make sure we don't make a mistake. So I'm going to rewrite u because 4th root of x is the same thing as x to the 1/4. So what's du by dx going to be? 1/4 x to the negative 3/4. Very good. And we could do the rewrite of that being 1/4. Now, in this case, we don't have to do any substitution. So I'd be tempted to just leave it as a rational exponent, x to the 3/4. So I was going to end up substituting in. You might want to switch it to radical form, but I'm going to leave it like that. So there it is. So I go back over here, and I plug and chug my two pieces. You know, I'm going to stick, I know it seems like kind of silly, but I'm going to stick with the square brackets because maybe that will just like jog your memory. That I need to fill in the blanks now with the two pieces, and both of these are going to be functions. The first function is going to be in terms of u's, and the second function is going to be in terms of x's, and they're the derivatives of y and u. So the derivative of y with respect to u is 3u squared minus 8u plus 3. And the derivative of u with respect to x is 1/4 times x to the 3/4. So again, this one wants you to write your answer as dy by dx. Do you think you're going to get full marks if you're asked to state this as dy, leave this as your final answer? Did you find dy by dx? Is u still showing up here? We want all x's, so you have to do that final substitution. This time it's in two different places. One needs to get put into both those places, a 4th root of x. And again, your call, you might just want to put in the x to the 1/4 version just to make it easier to simplify. So I'm going to write square bracket 3x to the 1/4 squared minus 8 times x to the 1/4 plus 3. And then, I guess I could just put, okay, too late. But 4x to the 3/4. Okay, and so can I now clean this up even more? I could write this as it's always good to have your single numerator, single denominator in your final answer. What's going to be in the denominator? 4x to the 3/4. And the numerator is going to be these three terms, but can you clean up the first term? X to the 1/4 all squared is really just x to the half. Yeah, x to the half minus 8x to the 1/4 plus 3. And that is acceptable. Fine. If you wanted to, you could change all of those rational exponents to radicals. Just be careful if you do that. Make sure it's visible, that I can know what's your exponent and know what's in the root. And just to clarify, guys, if you have to write 4th root, right, the 4 needs to be like in the root. Okay, that's where the 4th root shows up. Don't get lazy. You guys, you know what I mean? Like you can't put the 4 out there. And then here's the tricky thing. Like it doesn't really show up here, but it happens sometimes. And even I get confused sometimes. If it was like x 4th root of x, you guys get that being careful of where that 4 is can make it look like, maybe it looks like this. You see what I mean? Like the 4 just being a little bit outside might think, oh, it's x to the 4 times root x, which is wrong. You just got to be really careful about what your intention is when you write it. Be careful, okay? Because if I don't understand, I'm going to be like, what is this? I'm not going to be able to give you the full marks. Okay, so that's that one. Great. So now let's do B. If y equals 1/u cubed and u equals 2x minus x cubed, determine dy by dx at x equals 2. So the nice thing about this one is, you guys get, I just want the answer. I just want to be a number. I don't care really about what dy by dx is as on its own. I just really want the value when x is 2. So there's going to be a little fun shortcut in the middle here. You're going to like it, I think, hopefully. We'll see. So the first thing is we're going to do everything identical to what we just did. Dy by dx equals dy by du times du by dx. We're going to do our aside. Okay, so this time, y equals 1 over u cubed. Should I do a rewrite of that one? I have to take the derivative of y in terms of u. Hello. Sure, yep. Y equals 1 over u cubed. Should I do a rewrite of that to help me take the derivative? Let's all nod, smile and nod. Yes, we should. So what's the rewrite of 1 over u cubed? U to the negative 3. dy by du equals, so the u to the negative 3 derivative, same old power rule, u to the exponent, you bring the exponent in front, it becomes negative 3u to the negative 4. And if you rewrite this, again, don't make a silly mistake here. If I'm doing the rewrite here, what is there anything that stays in the numerator?
The negative 3.
Good. The 3 is, I want everyone to be clear, the 3 is not raised to this negative exponent, only the u is. So negative 3 stays on top, u to the 4 goes down there, and there's the derivative of dy by du. So for u, do I need to do a rewrite, or is du by dx pretty straightforward? I think it's straightforward. Du by dx equals derivative of 2x, derivative of negative x cubed. Beautiful. Ta-da. Okay. Copy paste time. I say that a lot, but do you guys get what I'm meaning? Like, there's lots of copying that happens here, and you're just gonna have to get used to it. So negative 3 over u to the 4 times 2 minus 3x squared. Can everyone see the usefulness of doing the asides? You kind of get all your rearranging, so you're not having to do that. You don't really have to repeat this over and over again simplifying. That's kind of annoying. Whereas if you do all your simplifying over here, it's nice and it's cleaner over here in your solution to have just final pieces. Okay, so here's the fun part. The question here does not actually ask you to tell me what dy by dx is. So I don't actually have to have a final answer that just has x's. So that means, though, that if I want to put 2 in for x, I still have a bit of a problem because there's this u here. What am I going to put in for u? If there was only something you were given that tells you, if you know the x, what the corresponding u would be. And I wish they gave you something that would say you input an x, the output would be a u.
The original equation.
Which one?
The u equals the...
Oh, isn't that literally a translator? You input x, output u. Well, that give you the corresponding u. Instead of me having to, and again, this one's not as bad, but like if this had like then u to the 7 plus u cubed plus u to the 3, or u squared, like there's a bazillion u's, and you had to put this in everywhere. That's like, and that's just going to be awkward. Whereas why not just get the number, just put the number in. Okay. In this case, again, it's a little boring. It's only one place, but you guys get it could be multiple places potentially, right? So here's what we're going to do. We're not done with our aside. We're going to do one more thing in the aside, and that is find the corresponding value of u when x is 2. So you guys know I've been allowing you that kind of fake function notation with y. So we're going to do the same thing with u. We're going to say, I need to find the value of u when x is 2. So u at 2 equals 2 times 2 minus 2 cubed. 4 minus 8 is negative 4. So now when I go over here, I just have to let x equal 2, u equal negative 4. I don't have to actually replace the u with this function. I can just replace the u with negative 4. Is this making sense, guys? Okay. So dy by dx is going to equal So I've got negative 3 over negative 4 to the 4 times 2 minus 3 to the 2 squared. The only important thing to remember at this last step is to put u in the right spot and put x in the right spot. Don't mix those up, that would be bad. Okay. And then clean this up, make this a single number. So let's deal with negative 3 over, anyone know what negative 4 to the 4 is off the top of your heads? It's 256. 4 times 4 times 4 times 4, 256. Okay. Another, again, just giving you some little mental math devices. 4 to the 4 is the same thing as 16 squared. 16 times 16, 256. Okay. And then over here, I've got 2 minus 3 times 2 squared. 2 squared 4, 4 times 3, 12. 2 minus 12, negative 10. And so we end up with 30 over 256. And right now you're going to get 4.5 out of 5 from me. You can reduce that, can't you? What goes into 30 and 256? 2, right? 2. 15 over 120. So that's how that works. So you didn't have to actually replace the u with the algebra. Okay, do you guys get that's where things can get a little bit confusing. And again, I'm just gonna you can flip the page if you want, but I just want to show you something. Like again, the idea here is if I said find the derivative of, okay, I'm just gonna write this. I said, say, forget about this u business. I said, find the derivative of that. Is it a little daunting to be like, ooh? Now you can do it, and like you can do it. It's doable, and you will get the right answer. But the idea here is that you're going to, first of all, negative exponents are going to show up. You have to remember, make sure you do the correct exponents, and it's just going to be a lot more awkward, right? You have to collect terms. You're going to have to get it to be a single expression. Whereas this way, it kind of all came as a nice little package deal. Okay, am I making sense? Like, just to, again, to give you the idea, you don't have to write this, maybe before I do this. What would be, if I said you had to take the derivative of this, what would be your first go-to for this question? And I said you had to take the derivative of this right here. Rewrite it, and so x would be raised to the 3/4. X, so you got to be careful here. It's the x to the 1/4, but squared, so that's x to the half, and then plus 3x to the 1/4 minus 2. dy by dx, again, don't be writing this, this is just for your FYI, right? 3 over 4x to the negative 1/4 minus 2x to the negative 1/2 plus, plus 3/4. Are we already going, ew, this is not fun, right? Like 3/4 x to the negative 3/4. Is that looking like my answer here? Not really. Because what's the one thing I've been saying all along about my derivatives? What do I not want to see in a final answer for a derivative? And do we see lots of negative exponents? So, okay. So this would be a case where it might just be easy enough to just write them all with positive exponents and then try and get a common denominator. Does that make sense? So 3 over 4x to the 1/4 minus 2 over x to the 1/2 plus 3 over 4x to the 3/4. You already see it, like how this is the extra complication. If I wanted to get a common denominator here, let's do the easy part. What numerical piece needs to be in the denominator for 4x to the 1/4, x to the 1/2, and 4x to the 3/4 to all be a common denominator? What number needs to be there? The 4. And then, if you remember, the rule for this part is x to the 1/4, x to the 1/2, x to the 3/4. I need an x here that each of these can divide into. So it needs to be the biggest. of the exponents, what's the biggest of a quarter, a half, 3/4? Okay, so I'm going to just slide up for a second. Is my numerator looking pretty good now? Sorry, I meant denominator. Denominator is matching, right? But you get that now you have to make the numerator match by multiplying by the necessary piece to make that the denominator. You see how the added complication here, right? So what would I have to multiply 3 by to have this as the denominator? Right now it's x to the 1/4.
Switch to 3? No.
What's the rule when you multiply? If you want 3/4 to show up, I have to go like x to the quarter times x to mystery exponent equals x to 3/4. So everyone agree that's what I need. What's the rule about multiplying powers with the same base? You add. I need a number here that when I add it to a quarter, I get 3/4. What's the number you would add to a quarter to get 3/4? 2/4 or half. So you'd have to have 3x to the half minus. So the next one is x to the half times mystery power is x to the 3/4. So this time you have to almost do, okay, well that's 2/4. 2/4 plus what is 3/4? 1/4. And this time I need the 4 because there was no 4 here. So I'm going to have to go 4 times 2, 8x to the 1/4. And then this one's the only one that's all good. It's all good to go. And voila, we did it.
Whoa.
But was it a lot more complicated? Is there a lot more places you could make an error? So it was nice, like if you now look back at this, it might look a little weird, but again, it was like simple, simple derivative and simple derivative, and it was like the derivative part was easy, and the cleanup was like kind of because it was a package times a package, and everything was already packaged for you. It was nice. You didn't have to worry about getting that common denominator. So that was the usefulness of that question. So I'm not going to redo the same thing over there, but you get it's the same idea that if you can deal with two smaller separate things that are easy, then it's easier than dealing with one complicated thing. All right. Okay. So to end this off, we're going to do a couple of sample thinking questions just to put it all into perspective of what we've been doing with chain rule. So the good news is there's no Leibniz notation here for these next two. Yay! But we still need to know how to do this. So this is an interesting type of scenario. So it looks a little daunting to start with, but let's just read it and see what's happening. It says, determine f prime at 3 for f at x equals g at h at x, given that g at 3 is 5, g prime at 3 is -2, g prime at 11 is -9, h at 3 equals 11, and h prime at 3 equals -5. Okay, so the one thing to notice about this question is, do we have any idea what any of these functions are? They're all mysteries. They're all like mystery functions. Okay, we don't know. So if you don't know that, then I have to give you something else in return. Like I can't give you nothing. So here's what you get in return. You get a menu. Almost think of it like a menu, okay, of specific values for specific function values and for specific derivative values. So it's in a sense what we want to do is we want to take the derivative of this in general with using just function f, function g, function h, and then as we proceed through, we're going to be substituting in 3 and then seeing what plays out if we apply the rule correctly. So you'll see what I mean when we go through it. So here's the derivative. Here's what f at x is. Our goal is to find f prime at 3. F at x equals g at h at x. Before I can find f prime at 3, I need f prime at x. So it's in generic form, but this is, you guys get generic form is rule form, right? We talked about the general rule at the very beginning. If I have g at h at x, I want to say, I don't want you to take the derivative of that. What rule is applicable here for this expression? G at h at x, chain rule. And the outer function is g, and the inner function is h. So g at h at x is, I need the derivative of g at blah. So g at blah, what's the derivative of g at blah? G prime, right? At, when I write the blah, do I do anything to it or I just copy it? You copy this. I'm not done, because what else do you have to do for chain rule? Times derivative of the inside, blah. What's inside hx? What's the derivative of h at x? H prime at x. If you go back to yesterday's note when you went in the box of what we said the chain rule was, it's literally that, just f and g instead of g and h, but it's the same pattern. Okay? This is generic chain rule. Okay? Okay, this is going to be pretty cool, guys. Okay? So I need f prime at 3. So first, let's do baby steps. So if I want f prime at 3, everywhere there's an x, I need to put in a 3. Let's do that. G prime at h at 3 times h prime at 3. Ooh. Can I go to my menu now? What would I like to order, right? So let's see, what do I need? What do I need here to fill in? So the first thing I see is you guys get g prime I can't do anything with because I don't know what this number is yet. But do I have, can I look at my little list and have a replacement for h at 3? Is there anything up there that's h at 3? Oh my gosh, h at 3 is 11. So I can replace h at 3 with 11. So g prime at 11. I know, right?
I like that.
Okay. You want to save the? Let's just do that. That was so exciting. We're just going to only do that. That was like too exciting. Save. Let's get its own stuff. Okay. So now, man, if only I had g prime at 11 and h prime at 3, I would be golden. And this is where it could be a little cheesy, like, hey, wait, I do have those two pieces of information. G prime at 11 is -9. H prime at 3 is -5. And I gave you those two pieces of information to trick you. Not required. Okay, those two pieces. Okay. And so let's replace. So G prime at 11 is -9. H prime at 3 is -5. You just answered this question. So you have no idea what function f and function g and function h are, but I know that the derivative of f prime at 3 is 45. Okay. Pretty cool? Fun? Yeah? Okay, the thing, like the idea here is, guys, obviously if I give you this question and you get a number in one of these functions that's not on your list, okay, you did something wrong. That's not like make up h and h. Like you don't, like there's no making up. Like, I mean, if you got an 8, that means, uh-oh, I made a mistake somewhere. Okay? In the homework, there's a few of these, okay, for you to practice, okay? But again, this is something that, us math teachers kind of like to put on tests, okay, like maybe under thinking, okay? And just to give you another scenario that could show up, what if I gave you this? Maybe it won't be a chain rule question, but just to kind of, this is me thinking on the fly, so this might not work out. Let's try. Okay, so we're going to say, f at x, I'm going to do this, f at x squared, no, I don't want to do that, I just want to do this, sorry, lies, g at x squared plus 5 at x equals 3. Just do the sample one with me here. So it looks a bit different from, so basically my goal here is find the derivative of this. Okay, so forget about f for the moment. Here's a function, find derivative of that at x equals 3. Okay, so it looks a little different, but I'm going to ask you something. Is it still the chain rule? Is there still an outer function and an inner function? Okay, so if I want to find the derivative, okay, so here, I'm just to make life easy, I'm just going to go y equals this. What would be the derivative of y? Y prime, okay. So what would be the derivative of g at x squared plus 5? What's your, so outer function, g at blah. What's the derivative of g at blah? G. What was the derivative of g at h at x? G prime at blah. Who cares what the blah is? You just copy it. So g prime. So is the first step literally the same? It's just the blah changed, right? G prime at x squared plus 5. But I'm not done. Times derivative of inside. What's the derivative of the inside? Ah. So instead of the inside being a function, I've literally just told you a function, like just a generic function, it's a specific function. Can I put in 3? Watch the magic, guys. G prime at 3 squared plus 5 times 2 times 3. Oh no, I did this wrong, guys.
14.
Sadness. Okay. This is what happens when I think on the fly. 9 plus. Okay. Just change the if you change those to 2's, and this is why I check these before I give you a test. Enough. Okay. I would double check everything. So if those were all 2's instead of 5's, my bad. Those were 2's instead of 5's. Now what happens? Instead of 14, which is not helpful, it's now 9 plus 2, which is G prime at 11. Is that visible in my list? That's the key, guys. If I give you this, it has to be in the list. Okay? G prime at 11 is negative 9 times 6, negative 24. So just giving you an alternate situation that could show up. Okay? My apologies for making the error there. But we're human. Okay. All right, last example. You're going to love this one, guys. So find the x values where this function has horizontal tangents. This is a Bridgeford special, guys. I love these ones. Okay? Okay. So first of all, I think we're all on board that expanding is not an option. You do not want to expand this. You will spend the entire test expanding, okay? And you'll probably make some errors, okay? So let's not go there. So what are we going to do is we're going to treat this, okay? Again, this is all about the layers, like what rules are going to apply here. So f at x equals 2x plus 5 all to the 8 times 3x minus 11 all to the 4. Overall, that's an example of a what of functions, like what operation. It's a product of two functions. Do we know how to take derivatives of products? But so everyone, let's practice the mantra. Derivative of product rule. 1, 2, 3, go. Derivative of the times the
second
plus the first times the derivative of the second. Okay, so what you're going to notice is when you start taking derivatives, if I say derivative of first, you're zooming in on the first. What rule are you going to apply to 2x plus 5 to the 8? Chain is inside of the product. Okay. So let's do it. My advice, be like Beyonce, start to the left, okay? Okay. So, derivative of the first, blah to the 8. Derivative of blah to the 8 is 8 times 2x plus 5 to the
7.
Am I done?
No.
Times derivative of inside, derivative of blah, derivative of 2x plus 5 is... Okay. You are 1/4 done the derivative. 1/4. Okay? Derivative of first. What comes next? Times the... Nope. Derivative of first times the second. Copy the second. 3x minus 11 to 4. What sign comes next? Plus. The first. You copy the first. Times. Derivative of the second. Derivative of 3x minus 11 to the 4, or blah to the 4. Remember from yesterday, guys? It's an open square bracket. And what number goes in? 4, bracket, copy, 3x minus 11 to the, am I done?
No.
Times derivative inside, derivative of 3x minus 11 is, there it is, guys. That is the derivative.
Wow.
Okay. Now, big picture, guys. Remember, the goal is to figure out when this function has horizontal tangents. In your head, everyone should have like a go-to strategy. Horizontal tangents. When do horizontal tangents occur? When the derivative is 0. I want to be able to set this equal to 0. Is this not useful to me in this form to set equal to 0? What form is useful to set equal to 0? Factored form. We want to factor this thing.
So would you factor first and then pop in 0?
We're not popping in a 0.
Okay.
We're replacing f prime at x with 0, and then solving for x. Right? It's a little bit different than putting in 0. I don't know if that's okay, but okay. First thing is, we kind of did this yesterday. It just wasn't as big of exponents, but we have done this a little bit yesterday. So it's a little bit of a we have seen this, but let's do it again. You've taken the derivative. I want everyone to be clear. The derivative is done. There's no more derivative taking. You do not have to think of any more derivative rules. The rest is just cleaning up. The first cleanup step should just be, if you remember, monomials in front. We like any single pieces, collect them, multiply them, put them in front. So in the first set of currently 1, 2, 3, 4 pieces, what can come in front? 8 times 2, 16. Copy 2x plus 5 to the 7. Copy 3x minus 11 to the 4. In the second set, again, I have 4 pieces. 2x plus 5 to the 8, 4. 3x minus 11 to the 3 and 3. What piece can I bring out in front? 4 times 3 plus 12. 2x plus 5 to the 8. 3x minus 11 cubed. Okay. So I said this yesterday, but I'll say it again. It looks complicated, but at the end of the day, how many terms are there in this expression? There's really only 2 terms. Those 2 terms separately have lots of pieces to them. Remember, terms in an algebraic expression are separated by plus and minus signs. How many plus or minus signs do you see separating things? Just the one. Yes, there's a minus there and a plus there, but that's not separating pieces. Those are within the brackets. This is the only piece that's separating, package number 1 and package number 2, right? Those are the 2 separate pieces. And so therefore, I'm going to write something on the board here, and again, don't, it's an analogy, but I want you to understand. This looks complicated. You guys get it's essentially this though. Okay, if I just get rid of the complicated complicated bases, and I just let a be 2x plus 5 and b be 3x minus 11. It's literally me asking you, if you can factor this, you can factor that. Right? If you can factor this, you can factor this, because it's a pattern. Right? So what pieces are in common? So I'm not going to bother doing this. I think we can do it. So remember, even though, again, it's complicated, there's really just 3 chunks to each piece, so three parts of each product. There's the numerical part, the coefficient part, the 2x plus 5 part, and the 3x minus 11 part. So let's examine each of those in turn and take out what's in common. From 16 and 12, you could take out, what's in common with 16 and 12? 4. So I take out a 4. 2x plus 5 to the 7 and 2x plus 5 to the 8. You take out the lower exponent of the 2 because that's how many are in common. So I take out 2x plus 5 to the 7. 3x plus minus 11 to the 4, 3x minus 11 to the 3. The amount in common is 3x minus 11 to the 3. You have just written the GCF. That is the GCF, the greatest common factor. Now we need the leftovers. Okay? Whatever didn't get taken out, you need to put in place. You guys get, like, that's your template. There's going to be a part left over before the plus sign and a part left over after the plus sign. Before the plus sign, there was 60, you took out 4, the leftover piece will be 16 divided by 4, 4. 2x plus 5 to the 7. Oh, we took out 2x plus 5 to the 7. Don't worry about that. 3x minus 11 to the 4, 3x minus 11 to the 3. Uh-oh, there's one of those got left over, right? So there's a 3x minus 11 here. Over here, there was a 12, you took out a 4. What's left over? 3. 2x plus 5 to the 8. You only took out 2x plus 5 to the 7. Uh-oh. I need a 2x plus 5. There's an extra one. But 3x minus 11 cubed, 3x minus 11 cubed. Anytime you do a question like this, this is like your template of what should happen. Like, this is like the story of the question. This is like, and the next thing that happened is this. Like, what you should end up with is a GCF that looks like this and an expression here where the only things you should be doing is distribution, like distributed property. There should be no exponents on anything here. Because, do you guys notice that because of the way the product rule works, the exponents will always be 1 apart. If you ever write, like, you guys get, this is what happens sometimes, and it makes me so sad, because then you spend like 30 minutes on this question when you should have spent only like 3 minutes on this question. Okay? You, like, maybe not there, but let's say you're in the process of doing the derivative, and you forgot to put the 7. You know what I mean? And you're proceeding through, then technically if you forgot the 7, then there's only really 1 in common, and then therefore you would still have 2x plus 5 to the 6 here. 2x plus 5 to the 6. Are we already starting to freak out about having to expand that?
Yeah.
Do you see what I'm saying? But that should never have happened. That should be your clue. Uh-oh, I forgot an exponent somewhere. Okay? I forgot an exponent somewhere because these should always have exponents of 1s on them. Okay? Now, I can't 100% say that this will always be, these numbers will always be numerical. Like, there could be x's in them, depending on what's in each. I can't, you guys get the bases were like the linear here, so it made life a little easier. As soon as these are not linear, it could get a little more complicated in here, but it's still, there should still be no exponents. Okay? There are a few odd cases where you might have to actually FOIL, like first out in last, but that would be it. There should be no exponents on any brackets. That's just like, just as you're doing your homework, just to make sure. Okay, so I'm done, question mark? Okay, so expand just in the square brackets, because again, it looks nice, but it's not as clean as it can be. Can I get this to look like another linear factor? If I expand and collect, it should be another linear factor. So 4, okay, there's lots of copying that happens. So 4 times 3x, 12x. Don't do all the hard stuff and then forget to distribute correctly. 4 times negative 11, negative 44. 3 times 2x, 6x. 3 times 5, 15. So 4, 2x plus 5 to the 7. 3x minus 11 to the 3. Pièce de resistance. What's left over here? 12x plus 6x. 18x. Negative 44 plus 15 would be negative 29. Okay. Agreed? Yeah? Confirm? Calculator? I think that's right. Okay, right. So, factored form. If the question was find the derivative of f at x, there's your derivative. If I want to know where it has horizontal tangents, though, is that actually an easy conclusion step from what all the work you just did? If I want, okay, so if I want to know where this has horizontal tangents, again, what's the goal? Horizontal tangents occur when the derivative is 0. This is the derivative, guys. You have found the derivative. Derivative found. Woo! Derivative. Okay? Let the derivative, let the slope of the tangent be 0. So do you see that now I've turned it from being a function to being an equation? And what makes this so beautiful is you've done all the work to get the right side to be factored. Is it easy to solve polynomial equations in factored form? You guys all should smile and nod. Yeah, it's super easy. You just set each factor equal to 0. And so, how many numbers are going to cause this to be 0? There's the x for that one, the x for that one, and that's x for that one. They're all yucky fractions, but c'est la vie. And that's kind of why, notice in the question I did say where are the points, I said where are the x values. I'm going to cut you a bit of a break, because plugging these back into the original is annoying, right? But I just care that you found the locations. So find the locations. What's the number that would cause this first factor to be 0? 2x plus 5 is 0 when x is? Yeah. 3x minus 11 is 0 when x is? And 18x minus 29 is 0 when x is? Everyone knows the rule. It's like opposite constant over number in front of x is how you get these numbers. Ooh, look at that, guys. Isn't that fun? Okay. I should leave that for Mr. Chance. This is grade 9. Okay. So, there is one rule to go. Okay. But I have created a little practice sheet for you guys to show what you know. Okay. Now, there are going to be a few questions on this sheet. Okay. That are going to look like that, but they could look like this, but it could be with a denominator. And if you look back at your notes yesterday, we did it a few times. If this had been 2x plus 5 to the 8 over 3x minus 11 to the 4, it would look like that. Can we still proceed like we did? Okay. Well, we don't. The only problem is that's not a product. But based on what we learned yesterday, can I make this a product? You guys remember, what's another way of instead of having this in the denominator, what could be my rewrite so that it looks like a product? I bring 3x minus 11 up, and what's the key? I have to raise it to the
negative.
You guys get that? You can totally still do everything here. What's going to be the annoying thing, though? There's going to be some negative exponents. But again, look back at your notes from yesterday. You guys remember, you can still factor out a GCF. Remember, it's still the rule of the lowest exponent. Just thinking ahead, and again, if you took the derivative of this, what would eventually you guys get that a 3x minus 11 to the negative 5 is going to show up when you take the derivative of the second. Agreed? Mm-hmm. You guys get that's a lower exponent than negative 4, so that's the piece you would take out. Does that make sense? So, again, if I took the derivative of this, derivative of the first times the second plus the first times derivative of second. Negative 4, 3x minus 11 to the negative 5 times 3. Clean up. You guys get that this is going to be the annoying part when you do the cleanup. You're gonna have this to the negative 4, this to the negative 5, but there's still a common base. You take out the lower exponent. What's lower, guys? So you take that out, and that should leave just a 1 left here. You guys get the part in the square brackets will still be nice. There should be no negative exponents when you do this correctly. Okay? And the good news is there's examples of that in this lovely show what you know. Okay? And then here's the extra good news. On Monday, I'm going to show you an alternate way so you don't have to do this every time. The way I'm going to show you on Monday requires no negative exponents. So if you're not a fan, there's a reprieve coming, but it's good to practice. Just practice the harder version, and then you can go to the easier version if you like. So I'm going to hand this out, and look at all the extra time you have to work. Sorry about that. I guess I'm a big liar. But it's all good. Hopefully, this weekend, you can chain yourself inside and do some chain rules. And Monday, we'll finish up the lesson, the unit for this part of the unit. Thank you for listening. All right.